Hey guys, so in this video we will be talking about the photoelectric effect, which was an experiment that happened in the early 1900s that Albert Einstein in 1905 explained. And in fact, in 1905, Einstein also published his special theory of relativity. But interestingly, in the 1920s he won the Nobel Prize for his work of something he did in 1905, but that Nobel Prize was actually for this photoelectric effect. It was not for relativity. So this is a very, very significant thing that Einstein did, and it's going to be one of the major things that pave our way into quantum mechanics. And so we have our experimental setup here, where we are shining some light at a sample of a metal. And the reason I have these electrons here is we're really focusing on the electrons in this metal, right, that we are shining the light on, and seeing what happens to the electrons. And so we have a sample of a metal, the light is shining onto the electrons, and then we have a wire from this side over here. And let's, I'll put on a simulation to show what happens when you actually shine this light. And then we'll see Einstein's explanation of what happens, which will end up being incredibly important for quantum mechanics. So we have our setup here, and I've got two graphs here. So we're going to be graphing the current versus the light intensity. So the light intensity, which is the brightness of the light, how much light we're getting out, and then the frequency of the light, or sorry, we'll be plotting the energy of the electrons that come out, which we'll see in a second, versus the frequency of the light we shine on it. So let's start. We've got a sample of sodium here, and we have a high intensity light here. As you can see, we've got a graph, and it's a perfectly direct graph that current and intensity of the light are related. And what's going to happen is we shine the light, and it actually sends electrons from this side to this side. And how we can measure that is then, right, this side loses electrons, which means it will get a positive charge. And then we have the negative charge of the electrons on this side, which will then travel through the wire back to this side from the negative to where we have it positive now. And then we can measure the current, and that tells us how many electrons are going through at what rate. Now we can adjust the frequency of the light that we use. And notice what happens as we change the frequency here, right? At a certain point, as we get around here, no electrons come off at all. But then we go a little bit down, and we'll start getting some electrons. And the speed of the electrons is proportional to the frequency of the light that we use. Not proportional to the intensity. In fact, if we change the intensity, look at what happens to the speed of the electrons. Other than having zero, as long as we have some intensity, we have more intensity means more electrons will be coming out. But more intensity does not mean the electrons will be going faster, which may seem weird, right? You would think that the more intensity, the more light you put on, the more energy those electrons get. So now we have the job of explaining this. Now, one other thing I want to point out is if we change the metal, so let's say we go with zinc, and we adjust this, what you can see is it actually has the same slope here. This slope on the energy versus frequency graph is the same. The only thing that's different is this x-intercept. Same thing if we change the metal to copper. Same slope, just different x-intercept. Platinum, same slope, but different x-intercept. So that's going to be another thing to look at. Okay, so we know now, just historically, we know that light behaves as a wave, and that's we know that from the double slit experiment, which we'll talk about in the next video. But in the next video, we'll really talk about it in terms of like electrons. But light does behave as a wave. We've known this. We've already shown this in the early 1800s, actually. Thomas Young showed that light is a wave. And James Clerk Maxwell also showed that with his equations of electrodynamics. So now, or electromagnetism, sorry. So now, Einstein is going to say, but light also behaves as a particle. And this is Einstein's explanation. So I'm going to give his explanation and then show why that gives the results that we got. But first, I'm going to quickly draw our graphs here. Our graphs. So we've got our first graph is going to be intensity of the light, and then this is the current. Right, and the current is proportional to the number of electrons, which is going to be important. The number of electrons in the wire. Right, and it does have to do with the speed that the electrons are going, but we're going to say at a constant frequency, or so at a constant speed of the electron, at a constant average speed, the current is proportional to the number of electrons in the wire, which should hopefully make sense. Okay, so this graph you should know, right? When we're doing an experiment, you've got to have controls. So we are holding here. We're holding the frequency of the light, which will show the speed of the electrons will be constant. Then we're graphing T, which is the kinetic energy, which we use the letter T, of the electrons, versus the frequency of light. Okay. And when we do this, we get these lines. So for current versus intensity, and again, I just want you to remember we're holding, I'll even write that. Holding electron speed, or holding the average, so the electron average speed constant. Okay, so yeah, so we're holding the electron average speed constant here. Okay, and now when we have this other graph, that for different metals we have a different x-intercept, but we are always going to have the same slope. Okay, and I'm going to call this x-intercept f0. Okay, so now we can go on to Einstein's interpretation of this. So Einstein's interpretation is that light comes in these discrete packets, which we will call photons. And he actually took this a little bit from Max Planck's work earlier in the 1900s, and I believe 1901, where Max Planck showed that the energy of what's called blackbody radiation is proportional to Planck's constant h. That's where we got Planck's from, h times the frequency. And so Einstein said the energy of a photon, which I believe we've already talked about here, the energy of a photon is equal to h times the frequency of that photon, h being Planck's constant being about 6.63 times 10 to the negative 34th joule seconds. And so now we have light, right? A photon of light that is going to hit the electrons. And if you have an individual photon of light, an individual particle hitting the electron, it has to have enough energy to release the electron from the metal. The electron is held on, the metal is holding on to the electron, and there's some threshold energy that you have to hit the electron with to get it out, right? So we'll say to hit the electron off metal, the energy of the photon that hits it has to be greater than some threshold energy, which we'll call phi, this Greek letter phi, and this is going to be called the work function. Okay, and now the higher intensity, what higher intensity means is more photons. So I'll write that here. Higher intensity means more photons. Right? But each photon, right, there's a 1-to-1 ratio. One photon hits one electron, right? And this is where we get the fact that light is a particle, because it's not, you don't just have a lot of light, high intensity, that just will hit out a bunch of electrons. No matter how high the intensity is, if none of the photons, right, if we look back at our thing, no matter how high the intensity is, if none of the photons have a high enough energy, none of them will hit the electrons. Whereas if you have photons that are high enough energy, but if you have photons that are a high enough energy, but there's not a lot of them, so let's go down to having a high enough energy, but there's not a lot of them, you're still going to hit the electrons off, even if you have a very low intensity, right? So it's all, whether or not you hit the electron off only has to do with the energy of these individual photons, not the total energy, right? Because even if we could have more total energy here if we have a high intensity with a low frequency, but you have to have that photon has to have enough energy on its own, right? That's part of it being a particle. And so it doesn't matter if you have a ton of low energy photons, they're not going to be able to hit the electrons off. So this explains, right, that the current, the more photons you have, the higher intensity, the more electrons you're going to hit off. So this graph makes sense with Einstein's explanation. How about this next one? Well, we have to have some threshold frequency, right? And we'll talk about that. So let's look at energy here. That the energy of the photon. So let's do another color. The energy of the photon has to be, well, the first thing is it has to hit this threshold energy. It has to hit the work function, right? So the energy of the photon comes in, it hits the electron. It has some energy that it's going to expend, getting the electron away from the metal. And then the rest of the energy is going to be used as the kinetic energy of the electron. So this is the kinetic energy of the electron, right? And so this makes sense. The photon, all of its energy goes into either hitting the electron off the metal, which is, right, this work function, and then the rest of it is put into the kinetic energy of the electrons. And we're looking at the average kinetic energy, because again, not all these photons will have the exact same energy, similarly, so thus not all the electrons will have the exact same kinetic energy. And so this is how it would look in the particle picture, where you have one photon come in, it expands energy to hit the electron off, then the rest of the energy goes into the kinetic energy. Now, you can also see through this that the energy has to be bigger than the work function, because the kinetic energy of the electron can't be negative. If it is, that just means the photon just doesn't hit the electron off, and none of this happens anyways, because there's no, the photon doesn't react with that electron. Or doesn't interact. So now we can rearrange this to sort of get our graph here. We have the kinetic energy of the electrons is going to be the energy of the photon minus the work function. And if we write this in terms of frequency, right, we have that the T is the energy of the photon is the frequency divided by, or is h times the frequency, so hf minus v. Okay, so this is our equation here for the picture where we're looking at an electron coming in. Hopefully this makes sense how we got this equation from assuming that we have these individual photons that have to knock off the electron, one photon, one electron. And now we have this equation, and if we solve for the x-intercept is when kinetic energy equals 0. The kinetic energy equals 0. If we want to plug in this point, if we plug in this point f0, comma 0, so the frequency is f0, we can see that this x-intercept f0 is equal to phi over h. Right? Hopefully you can see if you graph this, that the graph will hit the x-axis at a frequency phi over h. Okay, and again, you can do the math for that. Hopefully you know how to find the x-intercept of a graph, you just have to set t equal to 0, and then you figure out the frequency that causes t to equal 0. And that's going to be our threshold frequency, right? It's the work function, the threshold energy, divided by h, divided by Planck's constant. And this is exactly our graph. And in fact, the slope of this graph, the slope, is Planck's constant, which, as I had said, is the same for every metal. The slope for every metal that we look at, the slope is the same. So let's go back to sodium. The slope is the same. It just hits the x-axis at a different spot, which corresponds to each metal having its own work function, a different amount of energy that you need to hit the electron off the metal. So that's what this is. And so you can actually calculate these work functions, and then you can calculate the slope, and the slope is Planck's constant. So hopefully this makes sense as to how Einstein's explanation in terms of light being a particle does explain the photoelectric effect, right? You have this work function, you have this threshold frequency this light has to have, and everything else gets put into the kinetic energy of the electrons. So the simulation doesn't have the particle view where it shows what happens, but essentially what we have, right, you've got this thing, and it gives the electron kinetic energy as long as the frequency of this light hits the threshold frequency, and then all the leftover energy is going to go into the kinetic energy. So this equation. I'm hoping this makes sense, that you can see really that Einstein's explanation of this photoelectric effect produces the correct results. And so now we've seen our first instance of the wave-particle duality, where we see that light actually acts as both a wave and a particle. A wave, we know it already acts as a wave, and we'll talk about more of that in the next video, but it acts as a particle too in this photoelectric effect. So there's an interesting thing that we'll be exploring in quantum mechanics. There's one more piece of this that will be very important to talk about for the future in quantum mechanics, and that is momentum. That just as a single particle of light has a certain amount of energy, even though it doesn't have mass, it can still have kinetic energy, as we have seen, right? The energy of the photon is kinetic energy. And it also has momentum. And this is because when we're dealing with light, we also have to deal with relativity. And I don't want to go into relativity, but essentially what you can get from Einstein's theory of relativity that can help us explain what the momentum of a single particle of light, what the momentum of a single photon is the relationship. This is for massless particles only. So this is for massless particles. Einstein's theory of special relativity tells us this. It tells us the energy of a particle is related to its momentum by E equals pc, where p is momentum and c is the speed of light. And so the momentum of a photon is the energy of a photon divided by the speed of light, which is then, if we use this as hf over c. But now, we also have to remember, light is not just a particle. Light also has wave-like properties. It has a frequency, it also has a wavelength. And if you remember from mechanical waves, which I'll have the link in the description for my video on mechanical waves, we know that mechanical waves have a relationship between their frequency and their wavelength. That is, that the frequency of a mechanical wave times the wavelength lambda, f times lambda, is equal to the velocity of a wave. But the velocity of a light wave is the speed of light. So for light, this is for light, or for a photon, right? F times lambda is equal to c, which would mean that, let's just go f lambda equals c. And then if we look at what is f over c, if we sort of rearrange this equation, f over c is equal to 1 over lambda. So using this, we see that the momentum of a photon is h, Planck's constant, divided by the wavelength of the photon. And so that's going to be important. So not only do we have this equation, the energy of a photon is Planck's constant times the frequency, we have the momentum of the photon is Planck's constant times the frequency over the speed of light, which is the same as Planck's constant divided by the wavelength. So P equals h over lambda for a photon. The momentum of a photon is Planck's constant h divided by the wavelength of the photon, and that's going to be very important.